My name is Ken Visser, and I'm a professor at Clarkson University. And I'd like to welcome you to the Clarkson wind turbine test site that we have here. It's out near the Potsdam Airport. And what you're looking at behind me here is some of the equipment that we use to test wind turbines out here. Our primary research is focused on small wind turbine testing and development and design. And this particular test site was actually established in the early 70s by Dr. Keir from the Mechanical and Aeronautical Engineering Department at Clarkson. And his research focused on vertical axis wind turbines, such as this Darius wind turbine right over here. And you can see that it's a vertical axis machine, which means it spins around a vertical axis. This is a three-bladed configuration. And his research was trying to determine whether it would be feasible to develop this kind of turbine and mount it on wind silos, or farm silos here in the North Country. You can see one here. He built a small farm silo as kind of an example, and on the side here, if you just come around a little bit, you'll see part of the tower structure that was bolted to the silo, and it supported the Darius turbine here. So we kind of rediscovered this test site in the late 90s, and we decided to refurbish it and turn it into a small wind turbine test site to see if we could use it to improve the efficiency of small wind turbines. Big wind turbines, like the ones you see offshore, typically have an efficiency of about 51–52% out of a theoretical max of about 59%. But small wind turbines are not near as efficient. They're more on the order of between 30 to 35% is about the best you can do. So we thought this would be a great engineering challenge, trying to figure out how we could improve small wind turbines, and especially if we could improve them and make them more efficient, that would drive the cost down, and it might get more people to adopt wind turbines as a form of their energy supply, either for themselves or maybe for their farm or something along that line. So we started off with our first small wind turbine is right behind you there. It's a three-bladed Berge 1 kilowatt machine. Pretty conventional. In fact, I think you can buy it at Lowe's these days. And it generates about 1 kilowatt in an 11 meter per second wind stream, which is, roughly, 23–24 miles an hour. And that'll give you 1 kilowatt. So you can go and buy something like that today. I think it's about $2,500. And stick it on a pole, which is probably another couple $1,000, and that'll get you 1 kilowatt at about 24 miles an hour. And so our initial research aim was to determine whether, in fact, having three blades, such as the one you saw there, and which you see on the large turbines, is really an ideal type of situation aerodynamically. And it turns out that it isn't, and more blades is better, but of course they're more costly. But that cost model doesn't really apply to small wind turbines. So we set up two identical wind turbines here years ago, one with 6 blades and one with 3 blades, essentially to see if we could compare them and see if we could actually improve the energy output, and you can actually. So since that time, we've had a lot of people interested in coming out here and testing their wind turbines, and we've been helping people develop wind turbines and small turbine testing strategies. And I'll just kind of walk you out here to one of the examples that we have currently running. A couple of years ago, a company from Rochester, New York, came here and asked if we would test their wind tamer design. That's the blue one that you see here in the foreground. And we did. And we kind of evaluated how well the turbine behaved and compared it to our computer models and things at the university. And then we offered to improve their design, redesigning the blade and trying to improve the efficiency. And the result is what you see in the background there is their latest design of their turbine. This is a ducted wind turbine, a little different than the open rotor configuration that you saw from the Berge, because the entire rotor is actually enclosed in a duct. And the idea is to improve the mass flow through the turbine and hence improve the power that's extracted by the turbine. So we'll walk over there a little bit and you can get kind of a closer look at it. of the rotor blade. The flared end is actually the downstream end. If we come around the front here, you'll see the upstream end, and you'll see the rotor spinning there. Not only serves to increase the power output, but it also helps to align the turbine with the wind. And so this is their current design. We're testing it for them right now. The company's name is Arista Power in Rochester, New York. And we've also set up an additional anemometer and directional indicator on the top of the turbine. You can see that kind of sticking out of the top there. And the reason we do that is to try and measure the wind power, the wind velocity, the wind speed essentially, right near the turbine, and compare what the turbine is producing to the theoretical prediction of what the amount of energy is or power is in the wind. If you look back to their first design there, the blue turbine, you'll see behind that, maybe we'll just step to the side here, behind the turbine is the meteorological tower, where we have our instrumentation set up to record the wind direction and the wind speed at 3 different heights. And so the whole purpose of testing the turbines here is to determine how much power the turbines produce compared to how much power there is in the wind that they're intercepting, and essentially determine their efficiency or power coefficient, and that characterizes the turbine performance over a series of wind speeds. And so in order to do this, we have to take data for quite a while with different kinds of loads, and eventually we get enough data points that we can actually produce a power curve for the given turbine. So what we're going to do now is go back into the silo. That's where we have our equipment that records the measurements that we take out here and does the calculation of the power and the energy produced and that kind of thing. And one of the things I want to emphasize before we go in there is that right now we're not connected to the grid. We're completely off the grid. And the reason is we don't want the turbines to be connected either to an inverter to the grid or a battery source or anything like that. We're simply measuring the voltage and the current that comes off the turbines, and from that we can determine the power directly. And whatever you want to do with the power downstream of that is up to you. And that way we get essentially what the best performance is that you could expect out of a given design. Alright, we'll head back into the silo right now. Come on in. Okay, this is the heart of our data acquisition operation system here. This, of course, is an old farm silo. And we've completely gutted the place and put in a data acquisition system. And we have some computers here that are taking the data. And we measure the data every second, and then we write it right to disk, and at midnight we create a new data file, and so we get essentially a continuous stream of data, even though it's actually only 1 second long. And that enables us to take a look at 1 minute averages, 5 minute average, 10-minute averages, different ways to take a look at the data and to see really how the turbine is performing under different conditions. And with us here today is one of my undergraduate honor students. This is Andrew Salisbury, and he's working on a project right now to determine how the average wind conditions compare to if we were to characterize the turbine by an instantaneous measurements and then evaluate what the energy produced would be versus the conventional method of looking at an average power curve that's derived, say, statistically off a number of points and determining what the energy would be for that and whether there's a significant difference or not. So he's working on the data acquisition system here, writing a little more code, and this is his summer project here. And well, we'll just come in here, I'll show you a little bit more. So this is actually our data acquisition panel, and we bring in all the signals from all the different anemometers, temperature, pressure, humidity, wind speed. We bring all that information in here, and then from the turbines we measure, of course, the voltage and the power, and we bring that also in here. and then we digitize that and stick it on the computer here. And the nice thing about running the system here is this is all our own data acquisition code, so we can modify it any time that we want. If we want to add something or look at something different, we can certainly do that. And we bring the power from the turbines in here. So we actually have the capability to track 4 turbines at a time. We rectify the voltage, which is an AC voltage, into a DC voltage, and then we can measure the voltage and the current here. And we use a load that's simply a fixed resistive load. If you're going to swing around the back here, you'll take a look. We simply have a set of power resistors in here, and they simply dissipate the energy as heat. So there's no inverter connected, no battery connected, and all those kind of things can cause different kinds of performance on the turbine. So this simply dissipates the heat in a simple resistive load, which of course in the winter here in the North Country is kind of nice because it can warm up our little shed here and the students don't freeze. So that's about kind of in a nutshell really what we have here. We have the capability to test 4 turbines, and it's really kind of nice. We also have the capability to repair things too. On the other side here we have a little kind of repair area, but I think that's about all I have to say. I don't know. Andrew, would you care to comment?
Not much. This is my first summer up here, so I'm still starting to get to know things. The honors program has provided me with this opportunity to learn about this type of sustainable energy, and it's really opened me up to a new diverse world that is open to different types of engineers.
Okay, thank you very much.